Okay, this lesson is on AC circuits. So a sinusoidally time-varying excitation is a signal that has the form of a sine or cosine function. So sine or cosine functions variation with respect to time is exact same. Only difference is in its starting points. So sine function's value is 0 at time t equals to 0, or with the x-axis at 0, while the cosine function's value is at its peak at time or any x-axis variable at 0. And the circuits driven by sinusoidal current or voltage sources are called AC circuit. So here is the sine function we have. On this sine or cosine, you can say, so let's say I use my starting point of the function here. So x-axis can be an angle in degrees. We write it down with theta. Or it could be an angle in radians as omega t. Or it can just be time as well on the x-axis. On y-axis, it is the amplitude of the variable. It can be voltage. It can be current as well. And since we are drawing it as a function of t, so I'll just write voltage or current as a function of t. So let's say we begin with voltage. So voltage as a function of t. This value of the voltage function is called instantaneous value. So it is the value of the voltage at any instant. Instantaneous value. Now this value, the expression for Vt can be written as Vm sine omega t. You might see some of the textbooks or some authors using it a cosine form as well, but not any difference unless you're talking about the starting point. Okay, in this expression, again, we know the instantaneous value, and this value in here is the amplitude of the function. Amplitude of V, voltage. To label it on the diagram on this graph, so this is Vm. This value is Vm, so this height is Vm. And let's say on x-axis, if we label, let's say this is 0 degrees, this is 180, and before that, let's label at the peak value as well. So this is 90 degrees. That's 180. Similarly, negative peak of the function happens at 270, and here is 360. In terms of angle in radians, so this is pi by 2. That's pi. That's 3 pi by 2, and that's 2 pi. Okay, so instantaneous value, the amplitude, so that is how it is. And when you look at the variation of this graph, so let's say here is the angle in degrees, which we write it as 0 degrees, 90 degrees, 180 degrees, 270 degrees, 360 degrees. So angle in radians is 0, pi by 2, pi, 3 pi by 2, and 2 pi. And the value of the function Vt is 0 at 0, Vm at pi by 2, 0 at pi, negative Vm at 3 pi by 2, and 0 again at 2 pi. Okay, and again on this, one more thing which I want to explain right now is the time period. It's called time period. So time period is the time taken by any AC signal to complete one cycle. So one cycle is considered as, let's say you're starting from here and then you go through all the different values and you reach the same point. So you will see this point and this point onwards, it's the same value, it's the repetition of. So this is called one cycle. One cycle. And the time taken to complete one cycle is called time period, and we represent it with T, uppercase T, and of course the units are seconds. And since it's the time taken to complete one cycle, so that's how we can relate it to frequency of the AC signals as 1 over T, because frequency is cycles per second. So number of cycles completed in 1 second. And the standard unit of the frequency is also hertz. So frequency in hertz or cycles per second is inverse of the time period. Cycles in 1 second. Okay, so now also you can relate the frequency in hertz to angular frequency for rotational motions. Omega is the angular frequency and its units are in radians per second. If you have a frequency f in cycles per second or in hertz, it is equivalent to 2 pi divided by t as well. So that's radians, that's the seconds, and it's called angular frequency. Here I also want to introduce the 4-quadrant space in order to understand the angle. So this is the 4-quadrant space. Here is the angle 0 degrees. If you move counterclockwise, the angles are measured positive. That's so this is the 1/4, 90 degrees. This is positive 180 degrees. That's positive 270 degrees. At the same time, if we move clockwise, the angles are measured negative. So this is the 1st quarter, minus 90 degrees. That's the half, negative 180 degrees. And that's the 3/4, so negative 270 degrees. So here, negative 270 and positive 90 is one and the same thing. So for any of the locations for any variable, you will see any angle theta is equivalent to 360 degrees minus theta in its negative form. Okay, so that was about AC. Now we're looking at the 3 phases of the AC. So this graph shows 3 of those waveforms as we have explained with respect to only 1. And this is called 3 of those waveforms, and later on you will see that it's called 3-phase AC. Okay. Here, what is the difference? They have the same amplitude. Yeah, same amplitude for red, blue, and black. So same amplitude. And you will see that they also have the same time period. So from 0 to, let's say, 360. Here you are starting that late, or you can compare any other points, like you can compare this point and you will see that's completed in 360 degrees as well. So same time period T leads to same frequency F, or you can say same omega as well, because omega is 2 pi f. The difference is in their starting point, and that starting point introduces the phase of AC signal. So 3 characteristics which define or which characterize an AC signal is the amplitude, second is the frequency, and the third is the phase. So phase is the starting point with respect to 0. So in this case, let's say the black signal in here, we're saying, and what I'm going to do is I'm going to erase some information so that I can use the same space. Okay, so let's say the black signal is represented by V1, and we're gonna say it has an amplitude Vm, and it's a sine function, and the frequency is omega t, and do not have any phase because it's starting with this zero value of the signal at zero value of the angle or the time. Now for red, so for red, if you compare, red is starting by this much after zero, and let's take that angle as phi. Okay, any value, it looks like it's 90 plus a few more degrees, but let's take it as phi. So for red, let's take it as V2t. It has the same amplitude Vm. It is represented by the same sinusoidal variation. It is omega t. And for red, we will subtract that phi. Why? Because it's starting later after 0. Okay, similarly, if you look at the blue, this blue one here, and if you extend, it's gonna start before 0 somewhere. And let's say it has started maybe 5 degrees before 0 too. So then for blue, we will write V3t equals to Vm sine omega t, and this time, since that time is added to, so it's before 0, so plus phi. So this phi is the phase angle, okay? And phi is also called the phase shift. Okay, and based on that, we define these signals lagging or leading as well. So in this case, whoever has started early will lead in the race, considering all the players have the same capacity or same speed or the same ability to run. So in this case, we can say V3 is leading both V1 and V2, but you can define different angle. You can say here the V3 is leading V1, which is the black signal, by an angle of phi only. But at the same time, if you compare for V2, which is red, it's leading by 2 phi. Okay, it's leading by 2 phi. So how you calculate the angle? You calculate the total angle between the starting points. So between the black and the blue, it's 5 degrees. Between the blue and the red, it's 2 phi degrees. Okay, so lead and lag you define. If phi is greater than 0, which is in this case, it leads to a lead. And if phi is less than 0, which is in case of the red, that leads to lagging of a signal. So again, to summarize, blue is leading black by an angle of phi. Blue is leading red by an angle of twice as phi. Black is lagging behind blue by an angle of phi. Black is leading red by an angle of phi. Red is lagging behind black by phi. Red is lagging behind blue by twice as phi. Here we're going to compare two sinusoidal signals. Let's say V1t is given by 5 sine omega t. Omega can be anything. V2 equals to 10 sine omega t. So to say a few concluding statements about these two signals, they have same frequency, they have the same phase, both 0, and we call that in phase signals, and they have different amplitudes. One is will be having the value of 5 as an amplitude at, let's say, theta equals to 90 degrees. The other signal will have a value 10 in its amplitude at the same instant of time. Okay, so that's just comparing two signals, few things about them. Okay, now we're going to look at some trigonometric identities, and it's very important that you can look at them from my notes, or you can have any other resources as well, but we will be making use of them while using the phasor analysis, so we're going to make sure we have them handy. Sine A plus B, that's the first thing. Sine A cos B plus cos A sine B. Second is sine A minus B, which is sine A cos B minus cos A sine B. Cos A plus B, which is cos A cos B minus sine A sine B. And the last one here is cos A minus B, which is cos A cos B plus sine A sine B. Okay, so we're looking at the sinusoids in 4-quadrant space. This is where we have sine omega t. So let's look at the identity. And here we have cos omega t and sine omega t. Let's look at the identity, which is saying sine omega t plus 180 degrees. So positive 180 degrees, you go counterclockwise to add it. So sine omega t, you either add or subtract. So 180 degrees is there, so either you go there or you go here. You're reaching on the negative side of opposite side of the positive sign, so it's going to lead to negative sine omega t. Similarly, if this is cos omega t and you're adding or subtracting 180, so you're going to reach the same point as on the exactly opposite side of cos, which is negative cos omega t. If it's a sine omega t plus 90 degrees, so sine omega t is here, so you're adding plus 90 degrees. So plus 90 degrees is only 1/4, so you're going to lead to cos omega t. Similarly, if you're subtracting 90 degrees, so there you are, and you are at negative cos omega t. With respect to cos omega t, we are here, so positive 90 degrees, adding 90 degrees is going to lead you here, so positive 90, which is negative sine omega t. If you do cos omega t minus 90, so you're here and you're going to lead to positive sine omega t. So again, make sure you keep in mind all these identities as well. Okay, now we're looking at adding two sinusoids. And the two sinusoids given to us are, let's say, 3 cos omega t, adding or subtracting, in fact, my apologies, although you can change it to plus negative for sine omega t as well. So let's say you're doing this, so we're looking at what is going to be the result. So cos omega t, you guys know that it's on this axis, so we're going to have an amplitude of 3 on this axis. So let's say this is 3, and that's cos omega t. The negative sine omega t is this axis, so this is negative sine omega t, and it's going to take 4 steps in here. So let's say here is 4, okay, and in 4-quadrant space to sum up the values, so the resultant is going to be here, this will be the resultant. And you can use Pythagorean theorem to calculate its amplitude, which is 4 square plus 3 square root, which gives you 5, and this angle theta, well, you can calculate this angle theta based on the definition that you can have tangent theta defined in terms of any two of them, so this is 4, or you can also have so let's say we use tangent theta, so theta is going to be tangent inverse, the height is 4 and base is 3, and that gives you an angle of 53.1, and since it's a counterclockwise, so it's a positive angle, so here the result will be 5 to an angle of 53.1. so in this case, in writing where it is, so it's a cos omega t, and we're adding that 53.1 degrees to it. Okay, so for this blue position of the variable of the sinusoid has an amplitude of 5, and based on its location it's cos omega t plus theta, which is 53.1. so that's how we add two sinusoids. Okay, now we're going to do an example. In this example, we have a sinusoidal signal given to us as Vt equals to 5 sine 4 pi t minus 60 degrees, and we need to do a few things with it. The first thing, we need to calculate its amplitude. So its amplitude, if you're given that here the units are volts as an example, you can write the units with it as well, 5, but amplitude is 5. Then it's asking you to give the peak to peak value. So peak to peak value is from negative peak to positive peak. So you will realize it's double as the amplitude. So it's going to be 10. And then it's asking for the phase. So in this case, phase is negative 60 degrees here. So that's the phase, negative 60 degrees. We need to include negative 60 as well. And then it's asking for angular frequency, omega. So omega is this, so omega t. So omega equals to 4 pi. And the units here are radians per second, and you're always encouraged to have the value of pi substituted and calculate a number, a decimal number. So then we need to calculate the time period, the period t. The time period is actually 1 over frequency, and I did not calculate the frequency yet. And the next part is to calculate frequency. So frequency is omega is 2 pi f. Omega is 2 pi f. So your frequency is 2 pi. Oh, sorry, my apologies. Looks like I'm tired. Okay, so 2 pi times f. So f is given by omega, which was 4 pi, divided by 2 pi, equals to 2, and the units are hertz. And then you use that frequency here, so 1 over 2 gives you 0.5, and the units of the time period is seconds. So that was a small example to practice. Now we're going to be looking at phasors, which are used to represent AC signals. Phasors. So phasor is a complex number that represents the amplitude and phase of a sinusoidal signal. So phasor represents the AC signals. Phasor is one of the forms which you can represent the AC signals, but it only uses the amplitude and the phase. In the other form, which we have discussed earlier, that uses amplitude, frequency, and phase. So this only gives or uses the information to represent an AC signal in terms of amplitude and phase only. So it's a complex number. And there are 3 different forms for the complex numbers. First form is called rectangular form. And rectangular form, let's say z is one of the phasors, is x plus j y. So real part x, imaginary part y. Another form of complex numbers is polar form. And in polar form, z, the phasor, is given by r, the amplitude, and an angle phi. And the third form is the exponential form, which we don't use very frequently. Commonly used forms, especially for this course, are polar and rectangular forms. So in exponential form, z equals to r exponential j phi. So these are the three forms which we will alternatively use to have phasors. Okay, so phasor representation of any signal, let's say Vt, if voltage in time domain in time form as a function of time is written as a lowercase letter v, and then you use it as a function of t. So this in the phasor form to represent, we're going to use uppercase letter B, and then we're going to use a bar on top of it. Again, some authors use an arrow at the top, some authors use half of the arrow, some authors use it as bold letters to represent the phasors, but we will be doing this. And now I'll show you guys the time domain to phasor domain representation. Again, for more details, you can look into the notes. Okay, so here's how the sinusoidal functions in time domain are represented in phasor form. So if you have Vm cos omega t plus phi, that means a sinusoidal signal with an amplitude Vm, cos form, cosine form, and a phase angle of phi, that will be represented in phasor domain as Vm to an angle of phi. Now, whenever we are converting time domain to phasor domain for analysis purposes, so we're going to make sure if signal is given in sine form, we should convert it to cosine form using trigonometric identities, and then we can use it to change or to represent it in phasor form. Let's say Vm sine omega t plus phi, so we'll change it to cos first, Vm cos omega t plus phi minus 90 degrees, and then we'll say it's in phasor form, it's Vm, and the phase angle is complete phi minus 90 degrees now. Now, it's applicable for both current and voltages. That's why you have the current, the same analysis as well. Now, we use phasor diagrams to represent phasors. Phasor diagrams. On a phasor diagram, you have this as imaginary axis and you have this as the real axis. So since this is the real axis, that's where your 0 degree angle is. Let's say you have two phasors. One is Vm to an angle of phi, and let's say that is 45 degrees. And you have another phasor, let's say I equals to Im any value and to an angle of negative 30 degrees. Now I'll show you guys how to place that on this phasor diagram. So 45 degrees is positive 45, so that's counterclockwise or positive from 0. So 45 will be somewhere here, so this will be the phasor for V. Similarly, you also know when we go clockwise, it's the angle negative. So since the I is negative 30 degrees, so it's going to be from 0 to negative 30 degrees, that's going to be I. So this is angle 30, and it has to be clockwise, and this is angle 45 and counterclockwise. So that's how we do the phasor diagrams. Now let's do the phasor analysis for different circuit elements, including resistor, inductor, and capacitor. Okay, so first element is resistor. This is how you draw resistor in its time domain form. Let's say here is the voltage across it, Vt, and here is the current flowing through it as I in time domain. Let's consider It is given to us as Im cos omega t plus phi. So that's the base function. Using Ohm's law, voltage across a resistor is given by R times the current flowing through it. So that's going to give you R, and then you substitute for I. And here, so in terms of voltage, this together gives you the amplitude of the voltage. Now let's say we're doing the same analysis in phasor form. So here in phasor form, okay, so I from there in phasor form, I is given by Im to an angle of phi. Okay, and so from there, V is given by, if you see R, and that complete is I phasor. Okay, so that means for here, if you have voltage in phasor form, if you have current in phasor form, the value of the resistance remains R as it is. So in case of a resistor as an element, to convert its value from time domain to phasor domain, it remains same, R ohms. Okay, and we know that the voltage and the current are in phase in case of a resistor. When you look at its a graph on the as a function of time, you can also draw both phasors in phasor plane. Since both of them has an angle of phi as an angle of phi, so we will see whatever the value of the angle phi is. Let's assume it is positive 45 degrees. So you will see here will be your phasor V, and your phasor I will be in phase with the V. Okay, so that's for the resistor. Okay, so let's say for the capacitor, we have the voltage given as Vt equals to Vm cos omega t plus phi. And in phasor form, it will be V phasor equals to Vm to an angle of phi. Okay, so we know for capacitor, I is given by C dV over dt. So you do a bit of analysis, it comes to C Vm omega and negative sine omega t plus phi. So again we need to convert sine to cos, and that brings us Vm omega c cos omega t plus phi plus 90 degrees because it's a negative sign. Okay, so that's the expression for I, which let's say is given by Im cos omega t plus phi plus 90 degrees. And in phasor form, it will be I bar equals to Im to an angle of phi plus 90 degrees. So that means if you look at the phasor diagram, first of all, you're going to see, let's say here is the phasor space. If Vm, if V, not Vm, if V is here, your phasor for I is going to be leading by 90 degrees. So it's going to be ahead by 90 degrees. This angle is 90. So in case of capacitor, one thing is current leads the pure capacitor we're talking about. This is a pure capacitor, nothing in series in parallel to it. So current leads the voltage by an angle of 90 degrees. Another thing you see is, in order to have the value of this component in here, we're going to have V over I, which is the ratio of voltage to current. So that ratio, let's say, is the ratio of voltage to current, gives us, and both in phasor form. So that's the voltage, that's the current, so that's Vm over Im, and so it's Vm over Vm omega c. Okay, so that gives you this component as 1 over omega c, and of course to represent this 90 degrees it's going to be 1 over j omega c. So this component will be 1 over j omega c. So in order to change the value of the capacitor C in farads in time domain to phasor form or frequency domain, its value will be 1 by J multiplied by the frequency, angular frequency, multiplied by the value of the capacitance in farads, and the units here is going to be ohms, and this one is in farads. Okay, so that's for the capacitor. Now for inductor. Okay, for inductor, let's assume that I is given to us as Im cos omega t plus any phase angle phi, and in phasor form it will be I phasor equals to Im to an angle of phi. So now for an inductor, we know V is given by L di over dt. So you take a differential of I with respect to t, and that gives you Im omega times L times negative sine omega t plus phi. So change it to cos form. It will be cos positive omega t plus phi plus 90 degrees. Okay, so that's for V. Let's say this is the amplitude, cos omega t plus phi plus 90 degrees. And in phasor form it will be V phasor Vm to an angle of phi plus 90 degrees. And if you look at the phasor diagram, so let's again consider phi is 45 degrees around. So this is where what your phasor for I will be at phi positive. And since V is 90 degrees ahead, so V is going to be here. So this angle is 90 degrees. So for a pure inductor, current lags behind the voltage by 90 degrees. And also in order to have this element in here, what that is, so we're going to say V over I, which is Vm over Im, which is Im omega times L is Vm divided by Im. So amplitude wise it's omega L, since it's a 90 degrees phase relationship as well. So this element will be J omega times L. So in time domain, if you have L in henries, its value in phasor or frequency form will be J 90 degrees angle phase omega times L, and this value will be in ohms as well. So we're done all three elements. Now let's put together, see what happens with all of them. Okay, so in time domain form, the voltage source is Vm cos omega t plus phi 1. In frequency domain, and let's use another color marker. In frequency domain, it will be V phasor Vm to an angle of phi 1. I phasor Im to an angle of phi 2. R is gonna remain R. L is going to change too. So although the component will remain the same, but its value will be J omega L and the units will be ohms. The capacitor will itself remain the capacitor, but its value will be 1 over J omega C in ohms. And so what we do in order to analyze AC circuits, we use frequency domain analysis. What we do in there, we are given a circuit in time domain. We could be given it in frequency domain as well. So all the values in ohms and volts and amperes, of course. Otherwise, let's say a circuit is given in time domain. We convert it to frequency domain first, and this is all is happening at one frequency omega. Okay. Then here, so once you have the circuit ready, you analyze it using any of the methods like Ohm's law, KVL, KCL, nodal mesh, superposition, Thevenin's, Norton's, source transformation, whatever methods we have learned about or whatever methods we have learned with respect to DC circuits. You analyze, have the final result. Final result meaning the value of the variable we're looking for. And the final result has to be in polar form. Here, the final result has to be in polar form. Polar form like Vx, let's say variable we're looking at, equals to its value, V or Vx, to an angle of phi 3. This is just an example. So we calculate that, and then in the end you change the result, change the result in the frequency domain into time domain as well. How you do it? So you will say Vx t equals, you use the amplitude as it is Vx, you say it's a cos, you're gonna say it's at frequency omega, and if it's angle positive phi 3, so you're gonna say plus phi 3. So that will be your final step. That is how we're gonna analyze all AC circuits now. So we have one more thing in terms of AC circuits still. That's when we combine resistance, inductance, or capacitance, either in series or parallel, which is defined as impedance or admittance. So maybe a few more minutes and then we're ready to analyze AC circuits. Okay, so we're looking at impedance and admittance. So impedance, let's say for the time being, it could be any combination of resistance, inductance, and capacitor. And for the time being, we're going to just draw it with a rectangular box. Now let's say the voltage is V and the current flowing through the system is I. And this is the impedance of this circuit. Okay, so Z is a complex number, V divided by I. Okay, so Z is R plus minus, again, it's not only plus possible, it could be a minus as well, JX. Or you can also have it having an amplitude and an angle of phi, where the amplitude is given by R square plus X square square root, and the angle phi is given by tangent inverse X over R. Okay, so that's your impedance. Z is Z to an angle of phi for inductive circuit, and Z equals to Z to an angle of negative phi for a capacitive circuit. It need not to be necessarily only inductance. You can have inductance and capacitance, but inductive reactance will be larger than capacitive reactance in this case. Similarly, in case of capacitive circuits, you have capacitive reactance overpowering the inductive reactance. Okay, so the concept of admittance is the inverse of the impedance, or you can say it's a ratio of the current to voltage. So Y is the inverse of the resistance, which is called conductance, plus J, the inverse of the reactance, which is susceptance. So you might not have G equals to 1 over R or B equals to 1 over G. That's not how it is true, because ideally you have G plus J B equals to the inverse of R plus JX. So you're going to make sure that you convert it to polar and then to rectangular form, and then you can have G and B. But that is how the admittance and impedance are related. Thank you. Now we're ready to practice some questions on AC, and in next few videos we'll have just questions to practice, and we'll try to do that during the lectures as well.